So we've looked a lot at reactions of benzene by itself, and then we've looked a little, and we've actually spent quite a bit of time looking at benzene with a substituent on it. What do those same reactions look like in terms of ortho-para selectivity, activation, deactivation? What I want to do now is look at benzene with more than one substituent. That is to say, what if we have like an R group that I'll just label as R1. We put an R group here, and then we put a second R group here, versus if they're here versus if they are here, and then so ortho, meta, and para to each other. How are we going to see reactions occur? Versus what if we have reactions at or groups at multiple sites like this. So, I mean, and the list goes on. Okay, so how do we approach this? Well, we have to first do is classify the groups as electron donating and electron withdrawing groups. So we classify them as electron donating or withdrawing. Okay. So we've got them classified. As electron donating and withdrawing. And now what we recognize is that the strongest electron donating group will generally determine where a reaction occurs. Okay, so the strongest electron donating group will generally determine where the reaction occurs. Now, what's cool about this, it turns out, is that if, or let's put it this way, any electron donating group can override the deactivation by electron withdrawing groups. So that's pretty cool, actually. If you have electron donating groups, they can actually overwhelm the deactivation supplied by electron withdrawing groups. So, before I made a big point about how if you have electron withdrawing groups and if a reaction has to occur, we put it on meta, but for the most part, these things are just not good nucleophiles. These benzene rings, they've been deactivated. If you have multiple substituents and you've got one or maybe even two electron withdrawing groups on there, what's cool is if you put one electron donating group, that electron donating group will say, hey, I got this. I can supply the electrons for the nucleophilic addition in many cases. So don't worry about it, benzene. I know you've got a couple of electron withdrawing groups, but we can get through this. Okay, to understand these various situations, what I want to do is just kind of provide some abbreviations here. EWG is going to be my abbreviation for electron withdrawing group. Whereas EDG is electron donating group. Okay, so we have these two abbreviations. Now we can look at the various situations to see what is kind of expected to happen here. Okay, well, it turns out that in some cases, the groups can work together. Okay, so let's predict the products. We're going to keep this like super general. let's have an electron withdrawing group up here, and then ortho to it, we'll put an electron donating group, and we'll add an electrophile to this, and we'll say, what are the products? So the products would be, first of all, let's recognize that the electron donating group right here is going to activate the meta positions, which are here and here. Those red positions are meta to the electron donating group. Or excuse me, yeah, gosh, I have this backwards. I'm sorry. I just labeled the wrong thing. Okay, so there's my electron. Just have my colors backwards. I was like, what is going on? Okay, there's the electron withdrawing group. Sorry about that. Colors, I can do this. Okay, so these colors are meta to the electron withdrawing group. Now that's important to label because those are the positions that the meta directing electron withdrawing group will promote. Meta to electron withdrawing group, the electron withdrawing group will direct E plus to the meta position. Now, if we do the same exercise for our electron donating group now, in red, we see is it's going to go to the ortho and para positions. That's a weird way to do that dot. Okay, so there's ortho to the electron donating group. Here's ortho to the electron donating group, and here's ortho. Let's just get this taken care of right away. We're not going to see any reaction at a substituted center. This is an ipso center. It's that weird word I said. You don't see reactions at ipso centers because you don't have a hydrogen to lose after you've added the electrophile. So the electron donating group directs E plus to the ortho and para positions. Now, before we only had one ortho product, and I guess we still only have one ortho product, but realize if you have multiple substituents, you break the symmetry and you do have to draw both ortho substitution products. So the answer here, if we had to pick where our electrophile is going to go, well, the electron withdrawing group wants to take it to the green dots and the electron donating group wants to take it to the red dots. Other than that red dot at the center where we can't see a reaction occur, you notice that the red and the green are in agreement. And so we're going to see a product where we have our electrophile added ortho to the donating group and meta to the withdrawing group, plus one where it's para to the donating group and the opposite meta side. Both meta sides are now different for the withdrawing group because we don't have symmetry. So these are the two products. If we actually went into the lab, maybe one would be preferred over the other due to like steric hindrance or something like that. But that's not something I need you to worry about predicting. What I need you to recognize is that these are the two products that form and that no reaction occurs meta to the donating group and ortho-para to the withdrawing group. Okay, so they've worked together. That's nice. Now, what if we have this arrangement? Let's put the withdrawing group up here, the donating group meta to the withdrawing group. Okay. So red is the donating group, right? Green is the withdrawing group. So the green is going to go here, but now the red is going to go here and here. And I'm gonna go ahead and I'm just going to take some off that green dot. Oh, I was able, that's super convenient. Okay, cool. Okay, so I'm going to make that green dot nice and small. So there's the positions where the green dot is directing, and then the red positions are the ones where the donating group is directing. Now, what we have to remember is that donating groups are activating. And so because of that, they beat the preference or direction by the electron withdrawing group. So the donating groups are activating. And so what that means is these circles are kind of supposed to be helpful here, because if you add an electrophile to this, we have to recognize that the withdrawing group doesn't have that much say in any of this. It was nice that it was willing to work with the donating group last time, but the withdrawing group is deactivating. So it's not it's not really giving any electrons. It's not helping out at all. It's just, when we have to add an electrophile, we try to stay out of its way. But the withdrawing group is usually overwhelmed by the donating group in most cases. And so what we'll see is the electrophile beat the preference or direction by the withdrawing group and let the donating group take over. So we'll have an electrophile added here, which is ortho 1. We can go to the opposite ortho position of the electron donating group, which is down here. And then we can go para to the electron donating group. So these are our 3 products. And again, we don't worry about the ratio. We just try to recognize that, hey, we are going to form these 3 products. Okay, so the donating group beat the withdrawing group. Now, what if we have donating groups competing with each other? Okay. There's a few ways that we could have these arranged. I'm going to stick with para. So, whoop, that's not a highlighter. Okay. There we go. All right, so we're going to see activation at each of these positions now. And so if we add an electrophile to this, it turns out the left and the right are the same. So, man, off my game. Okay. An electrophile is added here. There's bilateral plane of symmetry on the left and right side. So we see if they are different from each other. I'm going to go ahead and label them. Sorry to do this. I'm going to label them 1 and 2, just so that we see that they're different from each other. We could have the electrophile here plus the electrophile down here. Okay. Now the ortho positions, so these are both like ortho adducts to one of the electron donating groups. Turns out the para position is blocked. If we had something like, let's look at a specific example now. Let's have 2 activating groups, 2 electron donating groups. One let's do through inductive effects, and the other one we'll do through resonance. Okay, so this is a medium electron donating group because it supplies its electrons by way of resonance and it stabilizes the intermediate in the electrophilic aromatic substitution. That's different from this one, which is a strong electron donating group. Having the oxygen directly bound to the benzene ring supplies the electrons directly through resonance. They are delocalized as a lone pair of electrons. We're actually pushing electrons into the system. Now, what this means is that if we have the strong electron donating group, we can consider that as kind of a nice, really impactful electron donating group. So we're going to see strong preference for these 2 positions. And then a tiny bit of preference for the ortho and para positions to the methyl group, because the methyl group's not as strongly donating. It hasn't made those positions as nucleophilic as the OCH3 has made its positions. Now, for the OCH3, we're going to see that one of those products that could form ortho on the CH3 substituted carbon, that one can't form, right? We can't add substituents to places that don't have hydrogens to lose. So the 2 products that we'll see dominate this reaction will be an electrophile that's ortho to the OCH3 plus one that is para to the OCH3. These are probably going to be your only products, but we'll just say these are the major products. Some possible minor products would be those that we see being ortho and para to the CH3. So here and here. So all products are certainly possible, but because we have drastically different donating abilities, activating abilities, we're going to see a clear preference for the products that are ortho and para to the stronger electron donating group. Okay. Now let's look at cases where we've got kind of a tie in the electron donating group ability. Let's say we've got, sorry about this, I get organized here with my page count. And I really like to focus on electron donating groups because I could teach you all day about strategies to think about electron withdrawing groups. Then you go into the lab and you actually try to do the experiment. You're like, what is this? This isn't working because the aromatic ring is too deactivated. Okay, so let's do a specific example now where we have, let's try this. Let's take this and we're going to add Cl2 and then AlCl3. You'll notice that these two are the same. Two CH3 groups. Okay, so if we have these, and it turns out they're not necessarily working with each other. That is, this position is activating ortho and para, whereas this position is activating ortho and para over here. Okay, so they're not necessarily working with each other, but due to symmetry, it turns out we're only going to see two products. Cl here plus Cl here. Now, if I draw the Cl in the other two spots, it's just the same. I mean, by symmetry, it's the same because the methyl groups are the same. Okay. Now, if we have an ethyl group and a methyl group, that changes things. Now, let's put those para to each other. Okay. Let's first of all consider these as very similar. Technically, they are very similar electron donating groups. Okay. They're not the same. The ethyl's probably a bit stronger, but you don't have to worry about that. You just say, oh, it's an alkyl. Okay, so I'm just going to treat it as though it's a CH3. Now, if we do Br2 and FeBr3, maybe I should be careful and not have a catalyst here. Let's just have Br2 present. Okay, now what we see is we're going to get ortho to the methyl group, and we're going to see ortho to the ethyl group as our two products. And I would just say no major and minor. We have pretty much the same ratio of the two. But now because we have an ethyl group on one side, we've destroyed one of the planes of symmetry, so we can have kind of that top BR ortho to the top group and then ortho to the bottom group. Okay, so here's a few examples. Don't worry about don't worry about like multiple bromination events or multiple chlorination events. If you saw before, you're maybe like, well, wait, didn't toluene, if you added Br2 and FeBr3, didn't it go to all the sites? Yeah, don't worry about that. That was just me illustrating how activated toluene was. I don't expect you to predict that product from scratch. Maybe explain why it occurs in a related system, but you don't have to like predict the product, if that makes sense, because that's a lot of stuff to try to, I mean, you basically have to go into a lab to make sure you understand what's going on. And we can't do that under these circumstances. Okay. All right. So that'll do it for this one. Next time we'll pick up with proposing a synthesis of aromatic molecules.